Okay, so this week we're doing conjugated diene still. And so firstly, we're just looking for actually identifying like pi systems or resonance structures. And so basically those are just whenever there is a double bond offset by like a sigma bond, you'll have conjugation. And so the important thing to kind of remember here is the sp2 carbons. So sp2 carbons are capable of being participating in conjugation systems. And so like these are all planar. And so all that conjugation really is just molecules that have that sp2 conformation. They're planar. And then that means that they have two p orbitals on either side. Remember the little dumbbells. And so electrons zip back and forth across that. And so by also being in that sp2 formation, it creates like double bonds on either side. And then because those electrons are zipping back and forth, it makes the distance of that sigma bond shorter. And so all that to say, the highlighted blue bonds, sigma bonds, are shorter than ordinary bonds, and that's because of conjugation. And so for this first one, there's two double bonds that are participating in that conjugation system and one sigma bond. For a benzene ring, all 6 of those carbons are sp2, and then whatever sigma bonds there are shortened to, be in conjugation, engaging in that conjugation. And then cool, kind of an important thing to remember here is there's also this hydrogen here, and that hydrogen does not have the shortened bond length because there's no double bond on the other side of it to kind of to bring that closer. So that's an ordinary double bond or sigma bond. Over here, these are all ordinary sigma and pi bonds. There's no conjugation in that molecule. This third one has got 1, 2, 3 double bonds that are in the pi system, and then those 2 sigma bonds that are in the conjugation system. So yeah, these bicyclic rings you'll get hopefully more comfortable with next week when we do more Diels-Alder. And then, yeah, so this guy out here is not participating in the pi system because he's locked out from the rest of the molecule. Yeah, as far as recognizing sp2 carbons, does anyone want to say what the electron geometry of this carbon is? Okay, it's sp3. I'm gonna hope you guys knew that. This one was sp2, and yeah, hopefully you guys are just really tired because we don't get a spring break and we're really far into this semester. But we're almost there, guys. Let's see. Next, we got 2 sigma bonds on either of these molecules, and we've got 3 sets of double bonds. Remember that just because it's on oxygen doesn't mean that it's not in the conjugation system. So oxygen here has 2 double electrons, lone pairs, and then also this double bond. So it's still sp2. It's still planar, and it's still participating in resonance because it still has these double bonds. So yeah, that's all for that whole first section. Are there any questions there? I'm not going to wait for forever because y'all didn't answer the question that I asked. Hopefully you guys can do this in your sleep. It's just adding, 1 butene with bromic acid. Yeah. And the important thing to remember here is cation stability. So this is an SN1 reaction. So yeah. From here, we're going into kinetic and thermodynamic products. We're not so much worried about that in the challenge problem, but it's important that you guys can do that and know how temperature affects it. So first thing is, I talked about this a lot last week. What is this carbon here? And please don't make this just like a 45-second silence.
Which carbon?
The one that's like I'm drawing an arrow to, and now I'm highlighting. It's a cation. What is that cation being stabilized by?
Is it resonance?
Yeah. There's a word I'm looking for.
Allelic?
Yeah. It's allelic.
Substitution.
Wait, say again.
Substitution.
Oh yeah. I see what you're saying. Yeah, like it's tertiary. So it's a tertiary and it's allelic. Exactly. So that makes it like the most stable type of cation you could think of. Good job, guys. That's that. As far as like whether it's kinetic or thermodynamic, that's going to kind of depend on. So when it's got cold temperatures, there's not a lot of energy available for basically rearrangements and for movements of molecules. And so that's where you get kinetic products, because kinetic is just like the least amount of movement. It's limited based on movement. Whereas the other one is thermodynamic. And so it's favored. So to kind of finish that kinetic thought, it's favored because it is the least number of like kinetic motion. It's favored by the least amount of kinetics. Yeah. And then the other one is favored by stability. So basically, you have an abundance of energy, and basically the reaction can continue to proceed. For a thermodynamic product, you could even see like once this kinetic product is formed, you have so much heat that this chlorine could fall back and reform this molecule, which allows for another opportunity for this alkene to come in and rearrange it. And so this is also favored by this substitution. So Zaitsev says that the most substituted double bond is going to be formed, and that's what we've got going on here. So yeah, that's all there is for that. Thermodynamic, you've got a ton of heat, and it allows for the 1,4 substitution, and then the other one is 1,2, and yeah, that's all there is for that. Any questions on any of this stuff? Okay, so as far as these challenge problems go, they want you to keep, they're basically testing 3 different concepts, and they want to make sure that you're not kind of mixing the waters with all those. I know in my first recitation, I kind of had talked about temperature some, and that was wrong. And I had said I would elaborate on it in this video, but now I'm elaborating on it and telling you not to worry about it. So yeah, basically all of this is testing to make sure you won't break Markovnikov rules with these initial double bond alkene attacks. And then basically just being able to evaluate that allylic carbocations are more stable than even tertiary. And then the last one is just basically evaluating that you can see that Zaitsev's rule applies. And so it's doing each of these individually. It's not having you mix these concepts.
So this is saying like an allylic carbocation. So the closer the carbocation is to a double bond, the more stable it's going to be. Correct?
So it's more about, I'm glad you asked that, because it's actually just about only if it's adjacent. If it's not adjacent, then it might as well not matter at all. So unless you have one carbon away, like here, and then like we'll say this is white, like that,
Yeah.
it's not going to matter. So like if it was, here, that would be incredibly unstable. Actually, that wouldn't even form, because if you have a double bond here, it's going to always favor the Markovnikov. And the Markovnikov carbon is basically the carbon that is going to be more stable when you break the double bond. And so the less stable carbon will automatically get that hydrogen. And the more stable one is going to form your carbocation. And so for this first one, the product of this first attack is this top left alkene. And then this, you can have a shift. So the alkene can flip around, and then you make a primary allylic carbocation. And I went ahead and labeled most of these. Oh, I just realized I didn't label this. This is a secondary allylic carbocation. And then this bottom one is can actually be flipped and rearranged, and it's the same thing either way because these two things are equivalent. So hopefully you can kind of see that. And yeah, so these two allylic secondary carbocations are the same, and they don't want you to mix up because internal double bonds are more stable, but they don't want you to worry about that concept when you're answering this first problem. The second one is asking you, or I'm basically just going to go over real quick what you could have done wrong if you had basically attacked these and formed a carbocation that is not stabilized by resonance, so it's not allylic. And so, like, for example, you put this hydrogen in a place where it blocks, this carbon or the carbocation from being able to get to the double bond. That's wrong. Don't do that. Nothing about that is ever right.
Yeah.
Yeah. And so this is the part C for that one. First of all, you just go ahead and do forming all the products. So I took each of those and had it get attacked by chloride. And once you've done that, technically the most stable one is going to be the one that has an internal chloride, so it's secondary, and then also has an internal double bonds. So those are also on secondary carbons. And so when it's asking about only the equivalency of double bonds, this double bond is on 2 secondary carbons, and then this double bond is also on 2 secondary carbons. So those two are equivalent. And that's all you really need to know for the first one. The second molecule is got a little bit more resonance structures. So once again, you can do each of these different double bonds can attack. And so if the one on the right attacked first, that's shown in green and then blue. And so the first one here is formed from right here. Once again, if you were to do this attack and then automatically put it on the tertiary carbon here, that would be wrong because it's not stabilized by this double bond. And so it's not allylic. And so that's the difference between tertiary and allylic carbons. And so allylic carbons are more stable.
Okay.
It's them more. And even if it is tertiary. And then once again, once you get into allylic carbons, secondary is more stable than primary allylic carbons. And tertiary allylic carbons are the most stable form of like carbocation. And so that's all that you really need to know. I went ahead and labeled each of these. So if you'd had this alkene on, or the double bond on the left attack, you would form the secondary allylic carbocation. And this would actually have like the most stable double bond. But we're not worried about double bonds right now. We're only worried about carbocations for this first part. And so, yeah, these are both secondary. These top two, or these two on the left, sorry, are both secondary allylic carbocations. And so they are both going to be equivalent and equally stable, equally stable. And then the most stable one is going to be the one that has is from the formate or shift or whatever of this allylic over here. And so you can actually form one of those tertiary allylic carbocations I was talking about. And then this other one is just a primary allylic. And so that's all for the first and second parts of that second molecule. Now we're just going to have all these chloride guys attacking. This looks kind of ugly, partially because I did it in a hurry and the battery on the pen was about to die. But anyway, as far as equivalency goes, once again, these two these two compounds or products both have 2 or secondary carbons that form the entirety of the double bonds. And so they're equivalent. The most stable kind of Zaitsev's product here is this bottom one. And so that's because you have a tertiary carbon bonded with a secondary carbon. So yeah, and then the least stable one is going to be the one with the secondary and the primary. And so if we're talking about, if we're concerned with the absolute most stable product, the most stable product in this is probably going to be this one according to temperature, because when temperature is hot, Zaitsev's rule usually takes control. But you guys don't really have to concern yourselves with that. And that wasn't really the scope of this recitation. I don't think ACS will test you on, you know, both the shifting and stability of carbocations and Zaitsev's products in combination with the thermodynamic and kinetic products, because there's like a whole rule in the ACS where basically they can't test more than like 2 concepts, I think, at the same time. And so that would be like well over 3. But anywho, that's all there is for this first for this recitation. So